In this video, I'd like to talk about the Nyquist stability criterion and Nyquist plots. So we'll look at how to draw a Nyquist plot and also how to use the stability criterion to assess if a closed loop system is stable based on the open loop contributions to the plot. So Nyquist, it really builds off of what we were working on with the Bode plots. It's a type of frequency analysis, and the main idea is to have an open loop system and have that information available to us, and then use that information to build a sort of polar plot, and then based on our stability criterion that we'll discuss in a little bit, decide if our closed loop system is stable or unstable. So the main idea is to build off of Cauchy's principle, which has to deal with complex contours, and build off of that and draw a contour, and then to use that contour information to map in a polar plot. So the Nyquist plots kind of look like this, and they have a kind of a round shape. And what you're going to do is you're going to come up with the bottom half of this plot, and then it's going to be reflected across the real axis. And once it's reflected, you'll be able to see the circlements. And we are looking for encirclements of this point, -1. This point, -1, is very special to us with the Nyquist stability criterion. And really, we'll see that in a bit, but our number /n of encirclements of the point -1 is half of the stability criterion right there. So we're building up towards basically the necessary and sufficient conditions for transfer functions for a closed loop system. Okay, so basically what we'll start off with is drawing a contour. Okay, and once again, the polar plot has the information of both the magnitude and the phase angle, what we were doing with the Bode plots before. We used both of that, and it contributes into this polar plot. Okay, so let's look at an example. So here we have a pretty simple example. It's got one pole, 1 over s plus 1. And we can really use either the j omega domain, or we can use the s domain for these. So I'll just go ahead and stick with the s domain here, and then we'll look at the omega in another example. Okay, so if I have this transfer function right here, I first note that I have a pole at s equal -1. So the first thing I would want to do is draw my contour. So the idea behind drawing the contour, and it's denoted with a capital gamma, is to include as much of the right-hand plane as you possibly can. Now, if you have a case where you have roots of some kind, poles or zeros, that are actually on the axis, on the imaginary axis, you can decide if you want to include them or exclude them. It's your choice. You can choose either the solid line or the dotted line, including a bit of the left-hand plane in the process. Both of these will result in different Nyquist plots. They'll look a little different, but you should be able to use the stability criterion either way and get the same result. So let's go ahead and draw the contour. So you can see that I already have a contour drawn out here, and I have our pole. So first thing I would want to do, looking at this transfer function, is to go ahead and pick out the pole. So I went ahead and marked that with an X, just like we did with root locus. The next thing I'd want to do is try to include as much of the right-hand plane as possible. Now, I didn't have any interference from our particular transfer function, so I didn't have anything on the imaginary axis that I'd have to worry about including or excluding for this particular problem. So I was able to go ahead and just include the entire right-hand plane. So this is a radius of infinity, and so all of it's included in our contour. Okay, so let's next pick a few points along this contour that are particularly interesting. I'd only want to really include the top right-hand quadrant for this because you can see the bottom half of this contour is exactly the same. It's just reflected across the real axis. So I'm going to choose a few points. I chose the origin, noted that as point A. Now don't worry about this, we'll go through and fill this out together. Point B, just midsection or some point along this imaginary axis. Point C, which is really the ultimate end of the imaginary axis, the maximum, point infinity. Some point D along the curvature, right here, with this radius infinity. And then point E, which is back to the real axis. And so that'll also be at a magnitude of infinity. Okay, so what I like to do, and you can see that I've done here, is to go ahead and pick out my points and build a little chart. And that kind of helps keep you organized when you want to draw your locus later. So I fill out the S values for each of these points. You can see that A is going to happen at 0, 0. So it's a 0 real value and 0 imaginary. So that right there, we just fill that in. For the magnitude and phase angles, we can fill that in as well. But if we plugged in the 0 here into the transfer function, then we would get the magnitude here. There's no phase for this value right here, because we have 0 phase shift. So our next point, B, this is on the imaginary axis. We have a 0 real value, and I just chose a value along the imaginary axis, something that I thought would be easy to work with, so I chose a 1. But really, any point would work. So if you plug in this value up here, you will get right here. If you want to take the magnitude, then you have to multiply by the complex conjugate. So I did that here, and then take the square root. That will result in the magnitude. And we can always refer back to our formulas that we discussed before with the Bode plots for the magnitude, and we also had a negative tangent formula for the phase angle. You can always plug values straight into those formulas and get these values. Here, I'm pretty much just looking at the contour and pulling values from that, but either way works. So here's our magnitude, and if I were to just identify that this is a right triangle, so I have this magnitude of 1 over square root of 2, because this is square root of 2, I have a distance of from A to B is 1, and then from A to our point is also 1. I can identify that as a right triangle, and I know that's 45 degrees right here. This is a pole, so it's going to be negative 45 degrees. And if this had been a 0 and we were looking at this from the perspective of the 0, it would be a positive shift. So remember, poles, or anything rather on the denominator, will imply a negative shift, whereas the numerator, the zeros, imply a positive shift. Okay. So just a quick note, just sidestepping this problem real quick. If we had some zeros up here, and we had some poles, other poles down here, we would have to go back and assess these points for each one of those frequencies, each one of those specific roots. And then we would deal with the phase angle summation at the end of that. And also with the magnitude as well. So it's actually you know, when you get a problem like that and there's a whole lot to do for a Nyquist plot, it's actually kind of uncommon to do it by hand now. You'll be doing it by computer usually. But I think it's of value to look through the technique and just kind of learn what you would do in that case. So that's why I think we'll do a few simple examples and then kind of learn how this goes. Okay, so back to this example. So we've got B filled in. Now for point C, we have the maximum. This is the infinity point on the imaginary axis, positive infinity. So that's our S value, J positive infinity, and a 0 real part. We plug that into our magnitude, and plug that into our transfer function to get the magnitude, and we would get a 0. It ends up being 1 over infinity. And we're actually going to see that happen for the next few points as well. If we were to assess the phase angle shift, so the C point is all the way up here at a 90-degree angle from our point. Remember, this is all the way up at infinity, so it's very, very far. This would be 90 degrees difference. And we can also plug that into our tangent formula, and we would also get the exact same value. And it's negative because it is a pole. But the tangent value, or the tangent formula, would give you that sign as well. Okay, for point D, we are all the way over here. I chose infinity and a infinity as well. So we're all the way out here, maximum real axis, maximum imaginary axis. And so if we plug that into our transfer function, we will get a magnitude of 0 again, and we will have a 45-degree phase shift. So we can see that it's actually kind of at a right angle if we consider both the infinity real part and infinity imaginary part. And again, it is a pole, so we have that negative phase shift. All right, last point, E on the real axis is at real value infinity. We plug that into our formula again, we get a 0 magnitude, and it's actually at a 0 phase shift. You can see that it is aligned with our pole. Okay, so we now have all the magnitude and phase angle values. So what we want to do at this point is draw our locus. This is our contour. It contributes to the information, but it isn't our locus. So if we were to draw this, we would have something that looks like this. And you may be wondering, well, okay, but these are supposed to have direction, right? Well, the direction should be going as omega increases. Our frequency increases, and then that fills in our locus. So in our case, we'll be going from point A to point B to point C and so forth. So the direction should be here, just like that. Now, let's walk through how I filled this in. So for point A, we had a magnitude of 1. And so we said that this was 1. And then we had a phase angle of 0. So it was just on this axis. Now, for point B, we had a magnitude of 1 over square root of 2, which is about 0.707. So I chose magnitude at about 45 degrees down. And then also kind of drew in the magnitude at what I would estimate 0.707 being. And so we've got these 2 points here. The third point will be at magnitude 0, so it'll be on the origin. And it would have a phase angle of -90. So actually we have all the rest of the points are at the origin as well. So this is point C, D, and E. They're all here. They're at different phase angles, but they're all at the origin. And so at the very end, after you've got all of your points mapped in, you can connect them with the Nyquist path. And so we are moving from A to B to C, and so that's going to be where our direction comes in. And the last step would be to reflect this across the real axis. So that you can see with the dotted line that I've made this, I've reflected this, and so now it's a completed circle. Okay, and so this is actually our Nyquist locus. So what do we do with this now? Well, we have this point, -1. Now, depending on what our situation is with this open loop transfer function, we can see if our closed loop system, which we don't have written out here, and maybe we don't have the information about it, well, we can discover if that is stable or not. And so we can talk about the stability criterion right now. Okay, let's pull that out here. And we'll do another example with the Bodhi plot data points. So real quick, the stability criterion, so we have a few different values to talk about. So number n is encirclements of that point, -1, where we were talking about right here. So you have a -1 point on the real axis. So this has to be encircled in the clockwise direction. So just like a clock would go, just like that. And we also have this number p. So p is the number of open loop, like from our transfer function that we're working with, open loop poles that exist in the right-hand plane. In our case, we didn't have any for this. Our only pole for this example was at -1. So our p, and we can just fill this out as we go, our p is 0. We also can see that we actually don't have any encirclements of this -1 point for our specific Nyquist plot. So we'll go ahead and fill that out as well. That is also 0. Okay, so finally, there's this other value, which is number z. And number z is the number of closed loop roots. So that's different from p. It's the number of closed loop roots that exist in the right-hand plane. So this really comes into play when you have already failed the stability criterion and you want to determine more information about your system. So our stability criterion is this equation right here. This is it. So number of encirclements of the -1 point in the clockwise direction should equal negative the number of open loop poles in the right-hand plane. So we should have the exact same number of encirclements. This negative sign results in a change of direction. So if we had, say, 2 poles in the right-hand plane in our open loop transfer function, then we would expect that we would need 2 encirclements of -1 in the counterclockwise direction. So it would change this direction. This negative sign results in that change in direction. And we'll use this in a moment and demonstrate it. So now the other detail about this is that we cannot touch that point with our locus plot. If we do, it's implying that we have at least one pair of complex roots on that imaginary axis, which we have earlier this semester determined that results in marginal stability as a best case. It can still be unstable, depending on if we have more roots. But if we touch the -1, we have at least one pair of roots that just lie on that axis. Okay, so let's say we want to go ahead and use this. If it doesn't work, if our numbers don't match for some reason, then we can go ahead and use this analysis formula. This will result in more information about the system, and we can actually see how many roots are in the right-hand plane. So, as we all know, closed loop roots in the right-hand plane equals instability. Now, we're talking about closed loop roots here. We don't have the closed loop transfer function written out. Be very aware that these are two different things, open loop and closed loop are not the same, but we can extract information about the closed loop from the open loop. Okay? All right, so let's use our stability criterion on the locus that we have just drawn. So we have 0 and we have 0. So we know we have to have this right here. So indeed, n equals negative p, and we are good to go. Therefore, we have a stable system. Okay, and that's really all there is to it. You have to have these numbers balance out, and that's really it's pretty simple from that standpoint. Let's look at another example though. So let's say now that we have gotten some data from a Bode plot. So our Bode plot has given us versus the increasing frequency, certain magnitudes and certain phases. Okay, so what I've done here is once I wrote out this chart, I went ahead and marked these points out. And so what's left for us to do is just connect these dots. So our movement is from A to B, B to C, and such, right in the direction of increasing frequency. So we're going to go ahead and try and connect these best we can with a certain kind of curvature. The B to C, just like that, and then from C to D, and then from D to E, and then from E to F, just like that. And so also I didn't mark it before, but let's say the -1 point is over here, and that should be about where it is, with the C point being at magnitude 50. Yeah, it's pretty close over here. But anyway, it's definitely inside this encirclement. Okay, so we're not done yet. First thing we'd want to do, draw our direction once we've connected those dots, and then let's reflect it across the real axis. Okay, maybe easy to mark first on the points where we have an axis crossing. So let's do that, and then we can just easily connect them. And just kind of do the best you can. With these, you don't have to be too exact. The idea is just to be able to use the stability criterion. And then we go ahead and continue our directions. So you can see we have this kind of double encirclement of the -1, and it's going in the clockwise direction, just like so. Okay, so let's go ahead and first assess what's going on with this locus, and then we'll come up with some different cases and assess the stability. Okay, so let's say we have a case 1, and our number P cases and our number N, which it just comes from the plot itself. Okay, case 1, let's say we have a P that is 2, and number N equals, of course this one is 2, just straight from the plot. Okay, all right, so we can see that we have the 2 and 2, but remember, we have to have the number encirclements of -1 be negative number P. Okay, so it's actually in the clockwise direction though. This is a clockwise number, and this is our stability formula right here, criterion formula. So we have 2 equals -2, and that can't be. This is actually unstable just because of the direction that the locus is moving. So it encircles -1 twice in that case. Okay. All right. So let's also say we have the case where we have no poles that are in the right-hand plane for the open loop transfer function. So we have a p equals 0. Again, this is going to be unstable just by this formula. Okay, but what if we wanted to use the analysis formula? So yes, we know it's unstable, but how many roots exist in the right-hand plane total for the closed loop system? Well, then we'll want to use our analysis formula. So we have number n equals z minus p, and this z number is the number of total closed loop roots. By the way, your book shows this as z equals n plus p. Either way, they're the same formula. So we want to see how many closed loop roots there are, and then we just plug in our number 2 equals z, and we'll just deal with this second case. This is case number 2. Z minus 2. And so we know that we should have 4 total closed loop roots in the right-hand plane, if that's the case. Okay? Now, where does this information come from? Where does this p come from? It comes from our open loop transfer function. So GOL, or the G of S that we're dealing with to begin this work, to begin this plot, that's where that comes from. Okay? So let's just look at a few more cases. So Nyquist plot. And many of the cases that we will encounter kind of have this general shape, and this is related to the golden ratio. So that's the number of phi, and you can look that up. It appears in Nature and a bunch of places, and it's actually a really interesting number. It keeps popping up, and actually the number 1 over phi is also special. So it'd be really interesting if you wanted to look that up and research it a little bit. But continuing this locus, okay, once it's reflected across the real axis. Now let's say that for this particular example, we happen to go in the counterclockwise direction with our increasing frequency. So it goes just like that, okay? Now, if we wanted to use our Nyquist stability criterion, again, writing out that formula should equal negative p. All right, so the conditions for which this is stable happen to be that anytime we have, let's say our negative 1 is 2, it is in here encircled 2 times. So we have 2 equal p, and that negative sign is, again, that means that we are going in the counterclockwise direction. So we write it as clockwise here and a negative sign right here. Okay, so as long as we have 2 roots, open loop, for the denominator, 2 open loop poles, then, so if we have 2 open loop poles in our transfer function, then this system is stable. So this is a good example of finding the conditions for which a closed loop system would be stable if you don't know what that GOL of S is. If you aren't given that, and you are given a locus plot, and of course you know this formula for the stability criterion. Okay, and so that's pretty much the main idea. Remember, if you touch the negative 1 with the locus, that implies marginal stability at the best case. It does not imply stability. We've given up stability at that case. If this formula right here fails for any reason, then again, that is also an unstable case. Otherwise, I hope that this helps, and I hope this has been informative. And you can always ask me questions if you have any questions about any of this. But we've covered 2 examples that are very similar to your homework, and that's about the level that I would ask on an exam. I really wouldn't expect for you to hand draw anything that I didn't give you tabulated values for. So really, questions about drawing the Nyquist plot would be more along this line, where we would actually take points and plot them. I think that that's just a little bit easier to do and to get the main idea across. But yeah.